Alright guys, so outline here what we're doing in this lab today. There are going to be a lot of similarities between this lab and the work lab that we did. The similarities will be you will have two desks with people sitting in them and a rubber band stretched between the two desks. And you will also be measuring how far back and with what force you draw the rubber band. That is where the similarities will end. I know that is a lot though. Okay, it does have a lot in common. After that, okay, you will be placing a Hall's carriage. That's what these are. Alright, they're crummy little carts that don't go very far or very fast. Okay, you can see the wheels are not very good. They're supposed to not be very good. All we want them to do is roll to a stop quickly. Right? Because what we want to do is we want to find out how much of the work that we do in drawing back the rubber band can actually be transferred in the real world to this cart. Right? We've done all those, catapult and slingshot and bow and arrow questions where it's the theoretical value of 100% of the energy goes to the arrow. Well, the real world is a lot different. All right? When you have a system that's basically a bow and arrow, okay, this is a Hall's carriage and a rubber band, but essentially the same thing. Okay? A lot of energy goes elsewhere. Not all of it ends up in the cart. So what we want to do is look at how much of it really does. Everybody follow me on that? To that end, there's a few things we got to record, there's a few things we got to calculate, things like that. We'll talk about that in a few minutes, all right? But that's going to be the general gist of this experiment. So, the problem we're investigating is how much of the available potential energy is converted into kinetic energy in a mechanical energy conversion. So, we're doing work and placing elastic potential energy in the rubber band. The rubber band is going to be released, at which point it will do work on the Hall's carriage. Because the Hall's carriage will begin to move, the Hall's carriage will have what kind of energy? Kinetic. All right? So we want to find out how well that transfer works. Okay? That is a mechanical energy conversion because we're going from work to energy, from energy to work to energy again. All right? There's several conversions that happen, okay, in this process. So we want to identify and explain the manipulated, responding, and controlled variables. So if we think about this experiment, what is it that we are manipulating in this experiment? What are we determining this thing has at the beginning? Okay, we're the ones that are, like, when we draw back the rubber band and we measure with the scale and the ruler, what are we putting into the system? Potential energy. Okay, we're the ones determining how much potential energy will be in the system. Right? That should give you a pretty juicy hint. The responding variable, okay, has to do with what happens at the end of this. Okay, and we're supposed to be comparing the stuff we put in with the stuff we get out. Your job to decide what are we getting out of this. Okay, controlled variables. Should these be pretty similar with a few additions to the work lab? Okay, is it going to be important that your desks always stay put? Yes. Okay, is it important to use the same rubber band every time? For the same reasons as the last lab. Okay, things like that. So think about that. All right. Should it also be important that you use the same one of these every time? Because they're not all the same, right? Some of them might spin better than others. This one spins pretty bad. Okay, some of them spin a little better than others because the bearings are better. All right. For our hypothesis, we want to generate a hypothesis that is a tentative answer to the problem and explain why it's so. So the big thing here, guys, is we should probably, in the if part of our hypothesis, okay, talk about the work energy theorem. Okay, and talk about what it says about when you do work and how much energy you get out of that work. All right, that's what the if part of your hypothesis should say, because that's the theoretical case for the work energy theorem. Okay, the and part again always describes the experiment. Okay, and then the then part, okay, should be what are we going to see? Okay, what are we going to see in terms of the movement of the cart? Okay, as we add more energy, what's going to happen to the kinetic energy of the cart? Okay, things like that. Okay, to the cart slash the energy involved here. All right, so there's several variables you're going to need to record in order to get all of these energies. Okay, you're going to need to record and calculate the potential energy. To do that, you'll need the mass of the cart, you'll need the force applied, and the distance you draw back the rubber band. So that's the distance force acts over. Okay? We'll just maybe write in there to remind us. Stretch of band. Okay? Just so we remember that's what that distance means, because there's two distances in this. All right? Then the kinetic energy. To do that, we need the mass of the cart. We need the distance traveled by the cart. Okay? And we need the final velocity, which for all of them will be 0, because they're all coming to a stop. All right? Now, here's the thing. Up until now, we've been calculating kinetic energy using this. Why can't we use that in this lab? Well, there is velocity, but we have no idea what it is. Is there any way for us to measure how fast that thing comes off of the rubber band? There's no way. Okay? I don't have a Doppler gun. I don't have a radar gun like the police have to shoot at your car as it comes off the rubber band. There's no way for us to measure that. So instead, what we're going to do is we're going to use the fact that all of the kinetic energy of the cart is going to be used up working against friction, because the car eventually comes to a stop. Agreed? Since it comes to a stop, we'll assume all the kinetic energy of the car was used against friction, or was used up by friction. And that's a safe assumption, because that is exactly what happens. All right, everybody follow me there? Okay, so in order to calculate the kinetic energy, we're going to do it a little differently in this lab than with this formula, because we can't use this formula. We don't know what V is. All right, so instead, we're going to have the mass of the car, the distance it travels after its interaction with the elastic, and how long it travels time-wise before it comes to a stop. So we're going to have the distance and the time for the cart. Everybody follow me? So there's a few things that we got to record while this is going on. Okay, you're going to have somebody with their phone's stopwatch recording how long the car rolls for and stop it when it stops. Right? It's not terribly difficult, but I mean, someone's got to be on the ball for that. Okay, we're going to have to mark where the car stops and measure that distance from the starting position. Okay, and record that as well. Okay, other things we're going to need, okay, or values we're going to need to calculate. The acceleration of the cart. So we'll know distance, we'll know the final velocity, and we'll know the time. So we're going to use a different formula than we would use in Science 10. It's actually one of our Physics 20 formulas, okay, but we can use it here just for this lab because I'm giving it to you. To calculate the acceleration of the cart, you will multiply the distance it travels by 2 and divide by time squared. Okay, and that'll give you the acceleration of the cart. Okay, the kinetic energy, like we said, we're going to calculate by using the fact that friction is what stops the cart. Okay, friction does all the work on the cart. So what we're going to do is find the work done against friction. Well, work is force times distance. Everybody with me there? Work's force times distance, and force is mass times acceleration, which is also on your formula sheet. This is the only lab where we actually ever use that formula. All right, so you're never going to need it on a test, but we're going to use it today. So that means mass times acceleration times distance will tell us EK. All right, so that's why we've got this here. All right, so there's a few calculations you're going to have to do. You don't have to memorize them. They're written right on here. It tells you exactly how to do each one. Okay, everyone follow me so far? So now, since we know the force we use from the force meter, we know the distance we pull back the rubber band, we know the potential energy that's in the system. We're going to use this formula, m times a times d, to calculate the kinetic energy the cart has after. How are those two numbers going to compare? How should they theoretically compare? In the perfect physical world, that potential energy and that kinetic energy should be, they should be the same. They should be equal. That isn't going to be the case today. All right, we're going to find that there's actually quite a bit of difference when we do this. If you get two numbers that are very close, you probably measured something wrong. All right, because the closest we've ever gotten in this lab was about 50% efficiency. All right, which means the kinetic energy was half of the potential. Most of the time, it's more like 20, okay, or less. If you get a kinetic energy value that's higher than your potential energy, have you definitely done something wrong? Yes, because you have broken the first law of thermodynamics and have created energy. You are not God, therefore you cannot do that. Okay? So if that does happen, you better check some of your numbers. You probably missed a decimal place somewhere. All right. Okay. And then potential energy, we said already we're going to calculate using force times distance. All right, the procedure I've already outlined for you. You'll put the rubber band between the two legs of the desk. Okay, you'll have a spring scale, draw back the elastic to a chosen distance, and record the force required to do that. Everybody with me so far? Okay. Then you'll put the Hall's carriage in there. Right? So you'll actually do a thing where you pull it back with the scale, measure the distance, measure the force, then let it go. Put the Hall's carriage in there and draw it back the same distance with the Hall's carriage. Okay? Everybody with me? Then you can let it go. Now, a couple things to do with this. You need to make sure that you put this right in the center of the rubber band when you're pulling it back. If it's off center at all, it's going to spin it. All right, because the forces won't be directly behind it. The forces will be applied more on one side than the other, and the only thing that will happen is this thing will spin out as it comes out. All right? We want to get it to go as straight as possible. If it goes slightly curved, that's fine. If it takes a hard right or a hard left, okay, right off the bat, you should do that trial over again. We want it to go generally straight. The first few times will be rough for you, okay? It takes a little while to kind of get the proper technique and everything on it, but trust me, you will get it. Okay, everyone with me there? All right, another thing you want to be mindful of is you want to try not to get the rubber band to rest on the wheels, okay? You can try and get the rubber band, okay, to rest. Well, there's really no way to avoid it. Try your best to get it up here rather than up here, okay? Because if you get it on the sliding part of the wheels, it'll just roll over, okay? Try and get it down here on the Hall's carriage so it's easier to pull back, okay? And your best bet for pulling back, okay, is to put your fingers inside the Hall's carriage when you pull it back, and then it's easy to let go, right? When you grab here, tendency is to pull it to one side or the other, okay? Little things to think about. You'll get it figured as you go. It's kind of a trial and error process. Okay, you're going to need some charts. Okay, we'll talk about the analysis here in a minute. So your charts are going to look like this. You're going to have trial 1, trial 2, trial 3, trial 4. Okay, your distance measured in meters. Okay, and this is for the kinetic energy. All right, so this is the distance the cart travels. Okay, the time the cart travels for. You'll calculate the acceleration using that formula on the previous page. Okay, calculate EP, calculate EK. All right, now the potential energy, the mass of the carts, okay, are 50 grams. All right, they're not heavy at all. 50 grams. Don't bother putting them on a scale. Okay, it just takes too long. They're all exactly the same. They're all 50 grams, so that's 0.05 kilograms. Okay, force read from the spring scale. Okay, you'll have that. Distance, how far the rubber band is pulled back, and then calculate EP. So this is what you would do in order to fill in this box right here for each trial. Right? For your kinetic energy stuff, okay, the mass is again 0.05. You got the distance traveled on the cart, so you don't really need this kinetic energy chart. You need this kinetic energy chart. Okay, where we got the distance and we got the time, the acceleration. Okay, and then this, remember, is MAD. All right, and this one here for this area here, guys. Okay, remember that we've got force times distance for this one. Okay. So you got a fair number of things that you have to record and a fair number of things that you have to calculate. So is this going to be worth significant marks on the lab report? Yes, so make sure that that chart is part of your lab report, okay? All right. Okay. Now, for the analysis stuff here, it says calculate the work done in pulling back the rubber band. Show your work. Is this part of that chart? It is, okay? Filling in that chart is actually not only part of your observations, it is also part of your analysis marks. So I want to see example calculations. All right, maybe make that that chart big enough when you hand in your final report that you can actually put the calculations in there when you're doing that on Google Docs. All right. Second thing, calculate the acceleration of the cart using your average distance and time. Again, show me your work. Okay. Calculate the kinetic energy of the cart. Again, it tells you how to do that here. It says C initiating and planning step 2B. All right. Well, if you go back Initiating and planning. Step 2B says I calculate kinetic energy by doing this. Right? So it tells you how to do each one, reminds you back where to go to do that. Okay? Outline how you determine the potential and kinetic energies of the system. Be detailed. Look back at the procedure because they pretty much tell you that in the procedure. Okay? The only question that's really entirely up to you is this one. Did the potential energy of the system equal the system's kinetic energy? Why or why not? Suggest reasons for your results. Okay? That's kind of the big analysis question. Everything else you're told how to do. All right? Then again, you got your conclusion, same as always. Evaluation, same as always. Okay? There'll be several sources of error here that are easy to identify, but remember, you have to think up ways to fix them. All right? And then the class discussion, remember, you don't have to do that, but we will talk about it as a class after you hand it in on May the 30th. Okay? That is this Friday that will be due. Questions? Alex. How did I do? Which one? This one here? Okay, this force is the force on the rubber band. You measure that with the spring scale. And this is the distance you draw the rubber band back. Okay, so this here, the potential energy is entirely the rubber band. The kinetic energy is all the stuff you measure about the cart. Okay, everybody got that clear? So potential energy, these are numbers for the rubber band. For kinetic energy, these are the numbers for the cart. Really, the only thing that you could get messed up is the distances. Okay, remember, the kinetic energy has to do with the carts, how far the cart goes, whereas the distance for potential energy is the rubber band. Okay, any other questions? Kendra? Yes, I can go back to the charts. All right. Oh, cart travels. So again, you didn't get them mixed up. This is EP and EK. So this is the potential energy column. Okay. What's that? Cart traveled distance, right? I just don't want you to get the distance for the potential, which is this distance here, okay, confused with this distance, which is about the kinetic energy of the cart. Okay. Any other questions? All right. So everything you need is up front here. The rubber bands are in this container with the spring scales. You want the 2,000 spring scales, and remember, in order to get the force, what do we have to divide the grams by? By 1,000. Sorry, no, by 100. Sorry, by 100. Sorry. Okay, everybody with me on that? Yes? Okay, so divide the grams to get the force, okay, read from the spring scale, this thing here, okay, that's going to be grams over 100, okay, and that'll give you your newtons. If you got questions during the lab, just ask, okay? I know you're not going to remember all of this, but just ask if you got questions. Okay, so you can grab your stuff, okay? Need 1 meter stick. Sorry, one other thing. With the carts on the floor, okay? You can mark on the floor where your carts travel to with the board markers. Just make sure that when you are done that you grab the board marker remover spray, okay, and spray those marks, and then you'll have to scrub kind of hard to get them to come off. Okay. The other thing you can do, sometimes this works, is actually mark over the mark again a second time with the marker again, and then it just wipes right off. Sometimes that works too. All right, but you're probably best to mark on the floor your starting position and where the cart ends, and then measure the distances. Okay, that way you don't have to worry if someone walks by and kicks the cart, you have a mark, okay, as to where the cart was during the lap. All right, let's say you're probably going to need 4 to a group here in order to do this effectively. Maybe 5, depending on whether you got people sitting in the desks to hold them still. Okay. All right, have at it there, guys. When it comes to the distances, you're going to pull that back. I leave that up to you. But suggestion, the further back you pull it, the harder the cart's going to be to control. Okay, so smaller distances, believe it or not, are actually better for the lab. I would say if you've got that thing pulled as far back as the spring scale will allow, you're going to have a really hard time controlling the cart. Okay, so probably small distances are better, and you need a 2,000 gram, not a 500 gram.